All right, so dehydration of alcohols. This is something we already know how to do. Again, so this is pretty awesome. If we have an alcohol, we do have an adjacent hydrogen in this case, and what we're going to do is form an alkene. And what we did was lost one portion of the OH and then a hydrogen, which makes water, right? Dehydration. That's where the name comes from because we lost water essentially. And this is called a beta elimination reaction because that alcohol is the alpha carbon and then that hydrogen is on the beta carbon. So we eliminated in the alpha beta between the alpha beta portion of the molecule, and we can do this with a strong acid as well as Pocl3 and Pyridine. Okay, and so the basically the first method we'll talk about is the strong acids. So super common strong acid H2SO4. Basically what happens is you have this alcohol and then you form an alkene and water, TSOH, paratoluene sulfonic acid. Same deal, right? As long as you have that beta hydrogen, then you can form an alkene product. Okay, and this is an elimination reaction, right? And so we want to follow the trend of elimination reactions. That means primary, secondary, tertiary. As we go from left to right, we are increasing in the rate of reactivity for this particular elimination reaction. Sorry, let me get my triangles right-ish. So remember, primary, secondary, tertiary, we have an increased rate of dehydration, and which is very specific to alcohols. And then in general, we have the increasing rate of elimination reactions, just depending on what our leaving group is, right? Old news, Jess. Old, but still lit. This is cool, right? You already know it. That's awesome. Shout out to Betty White. She makes me laugh. Um, So don't forget when we're talking about elimination reactions, we always got to talk about Sidestep Rule, right? And so remember, Sidestep Rule is basically forming the most substituted alkene. That's going to be the major product, okay? So if we have this particular alcohol with a strong acid, we've got options. We can do this particular alkene, we can do this one, and then technically the other alkene that would form is the same as the one on the right. So the tri-substituted alkene is the major product, while the other is the minor. Okay, so that's pretty straightforward, right? Like I said, old stuff, old news, but still lit. We have E1 and E2 reactions as options as well, right? So this particular alcohol is a tertiary alcohol, strong acid. Anytime we have a tertiary alcohol, we have the ability, and a strong acid like that, we have a weak nucleophile and a weak base. Okay, so as that conjugate, that's H2SO4. It's a strong acid, so that means it's a weak conjugate base. And so that water can leave, forming that carbocation. That means that now we have access to that beta proton and can remove it with this lame base, okay, forming the alkene product, as well as reforming H2SO4 and water left, because this is a dehydration reaction, right? So I like to think about water, right? So we did have water leave, so why not have water come in as that base and swoop on that proton, because it is a stronger base. And so you might see this sometimes as well, but we also got to remember that water plus strong acid forms hydronium and that conjugate base. So there's going to be, maybe there's water present, maybe there's not. We do have options though, as water could be that strong base that comes along, or sulfuric acid could be the source. The conjugate base could be the source of that base to come along and remove that beta proton. Either way, we got something coming along, right? This is a secondary alcohol now. Same process. We make that OH a better leaving group by protonating it, making it water, having that water piece out. And then now we have this secondary carbocation. Base comes along of some sort, removes that beta proton, and we get our alkene product. We get that conjugate acid of that base, and then we get water. Dehydration reaction, we always form water, right? So that was a secondary. Now we've got a primary alcohol, right? So we can't have a primary carbocation, right? And so Really, what that leaves us with is an E2 mechanism as the only option for dehydration of a primary alcohol. Okay, so if we have the same setup, primary alcohol, strong acid, we're going to get the alkene product just by, as well as the sulfuric acid and water, but it's just going to be a different mechanism. Okay, it might require a little bit more heat or just a little bit more energy to be put into this because we have a couple different factors that we want to talk about with this, right? So there's entropy and enthalpy we always want to talk about in a given reaction, right? So for entropy, in this case, it's favored. The reaction is favored in terms of entropy, but it's unfavored in terms of enthalpy. And that's because the pi bonds that are formed in the product are actually weaker than the sigma bonds that were originally there in the reactants, right? So the delta H for this particular reaction is actually positive 38 kilojoules per mole. And what that means is that this is an endothermic reaction. So we have to put energy into this system. And positive 38 is a decent number. But the cool thing about this one is super fun. So look at the starting material. This is an alcohol. It's got a higher boiling point than the products because we have the OH that can hydrogen bond, right? And alkenes, they can't hydrogen bond anymore, so they got that lower boiling point. They also, in this case, is a gas at room temperature. This is just showing you how drastic those boiling points are. Ethanol boils at 85, the ethene is a gas, and it pieces out, okay? Peace. My end. If you don't know about Martin, you should definitely find it. If you, I know you know about this one though. Bye, Felicia. So that gas leaves, it pieces out, and that actually makes this reaction favorable entropically. So it's entropically favored because as that product leaves, we are driving the reaction to the right. Okay, and so this is of course a general chemistry concept where if you like remove one of the products, you are driving the reaction forward via Le Chatelier's principle. Okay, and so this is a really important factor in this particular reaction. Now, although not every alkene product is going to be a gas, sometimes they're just liquids also, but they're lower boiling point liquids. So what we can do is, like this dude right here making moonshine, we can distill off that alkene product, and that is essentially the same idea, right? We're creating that gas and collecting it as a liquid and driving the reaction forward. Okay, so in this boiling flask right here that's bouncing up and down, we got an alcohol and an alkene, and as we heat it, we are boiling it, and that lower boiling point alkene leaves first, and then it can be collected. Sorry, this is I was trying to be fun with it, but then we're collecting the alkene product in this here cup or in this jug o' moonshine. Okay, so of course I'm not going to leave it at that. I'm going to give you a terrible drawing of my own, but basically the point is that you can distill off the lower boiling point alkene products. And again, they're lower boiling point because they have less intermolecular forces, i.e. hydrogen bonding is not in an alkene. It's not an option. And so here's my super cool drawing of a round bottom flask. And then we have a distillation adapter. And it could extend down like this, a little curve, and then you have another collection flask, right? And so here's my super awesome thermometer that allows us to determine the temperature of those vapors. It's 88 degrees, let's say. I just made that up. No significant number. But the flask on the left has the alcohol and the alkene, and as you heat it, the vapors of the alkene go up and they condense on, and then they condense into a liquid and they drip down into the flask on the right. And so that's why we get our lower boiling points liquids on the right. And then essentially this is a means of separation. So we're purifying our sample by boiling point and distillation. And so we might have like a water flushing through this particular portion. It's called a bridge. And then water in one portion and water out the other. And that allows water to cool those hot vapors and basically just drives them into the liquid phase phase and allows them to drip down into that collection flask. Okay, so that's distillation in a nutshell. I bet you didn't know people in the backwoods making moonshine were organic chemists, did you? Okay, moving on. So the other method is the dehydration with POCl3 and pyridine. Okay. Now, this is essentially the same idea. We have an alcohol, and we use POCl3 to convert the OH into a better leaving group. Okay, because we know hydroxides are terrible leaving groups, and so we do need POCl3 and pyridine to make that alkene. So if you see those, then you want to think alkene product. Okay, and we'll see other things that might look similar to POCl3 later, and so we just want to make sure that we understand the formula specifically, and it looks like this. So here's the mechanism, and the oxygen attacks the electrophilic phosphorus that kicks up the pi electrons to the oxygen. And we also have that positively charged oxygen. It's an oxonium, right? So the negative charge on that oxygen basically creates another pi bond with the phosphorus, and that kicks out that chlorine, as it is a good leaving group. And what we get now is pretty much the same thing, but with the phosphorus doubly bound to the oxygen, and now 2 chlorines on that phosphorus. Okay, so we still have that positive charge, and I do want to point out again that this is an oxonium ion, so it's a trivalent oxygen. So oxygen with 3 bonds has a positive charge, and it doesn't like it because it's pretty electronegative, right? And so we need to fix that. Anytime we have that, it's usually an intermediate. And we do that with the presence of pyridine. So pyridine is drawn here, and it is a base. It's a good base, and it removes that proton to neutralize that oxonium ion. So what we end up getting is this neutral species here, but now what we have is this beta proton on either side. They're symmetrical in this case. We just need to draw them always to make sure that we're making the right products. That removes that beta proton and kicks off that leaving group, which I said, remember POCl3 does make it a better leaving group, and it leaves as OPOCl2 minus, okay? And then an alkene product is formed. We also have this positively charged nitrogen species, which is called a pyridinium ion, and we have 2 of them from the deprotonation here and here in the reaction. So we got our alkene product, and we did it with POCl3 and pyridine. Okay, so sometimes, if you think about it, sometimes strong acids will react with another portion of the molecule if it's a more complicated molecule than like cyclohexanol, and so that's why we might need this method as a means to make the alkene product. Okay, so you'll notice that in organic chemistry there's lots of ways to make the same thing, and that's because we need a variety. We need more tools in our toolbox. Okay, we need to have variety in case strong acid will destroy a portion of our molecule that we don't want to get destroyed. Okay, so let's talk about practice. Okay, you want to talk about practice? You probably do, because you got to get this in to better understand these reactions. But let's say we have this alcohol. We got TSOH, paratoluene sulfonic acid. It's just a strong acid, right? We got another strong acid here with this particular alcohol, and let me give you one more. Okay, so we got this alcohol here with, let's say, POCl3 and pyridine. Okay, so pause the video, draw what you think the reaction products are going to be. Okay, though, don't forget about the different alkene products that you can form, right? You got this one right here in green. You can also form an alkene with the pi bond in red, but we're going to ignore that because they're the same, and we should be able to identify that pretty quickly. But this is a trans alkene product, right? And so we also need to draw the cis alkene product. Let me move this down to the bottom though, because we got to kind of go make our way down that way with that cis product. And so we got here, this is our cis alkene, and our trans is on top. So we know that trans is going to be the major product, right? because it's more stable. The large groups are as far away from one another as possible. We also have another alkene product in this second molecule. But since we've got more than one alkyl group coming off of that, it's different. We can form an alkene here as well. But then one more again, we can do another alkene product on the left side of that, but those are going to be the same. Okay, so same products here, but there are also the not just statistically the major product, but they are also the tri-substituted product. So that is the major product. And I say statistically because when you have like different options to form the same product, that increases the percentage of that product. If you want me to elaborate on that more, you can definitely ask me that question in office hours. But this is our product here for the primary alcohol with the POCO3, and there you have it. So let me ask you this question. I got you one more real quick. Let's say we have this alcohol and this strong acid. What do you think the major product is going to be? Draw the alkenes, right? What if I told you that the major product was this one right here? What, Jess? What are you talking about? This is the major product? Why am I being a major pain in your butt? Y'all ever seen Major Pain? It's a fantastic movie. You'll get no sympathy from me. This is organic chemistry. It's tough. It's not easy. It's not meant to be easy. This is that good stuff. So it introduces a really fun topic, okay? Now, before I explain it to you, I want to give you one more example that's crazy. So what do you think the product of this is going to be? I'm not even going to give you a chance to think about it because you're not going to get it right. It's this one right here, this cyclohexene product. That's wild, right? You have this crazy looking alcohol on the left, and then you get this 6-membered ring from a 5-membered ring. What you talking about, Jess? That leads us to a sweet topic called 1,2 hydride shift, how we get the product on the top, and a 1,2 alkyl shift, how we get the product on the bottom. So that 1,2 alkyl shift on the bottom was kind of crazy example. There are more simple examples. Okay, so the topic is carbocation rearrangements. So if you form a carbocation intermediate in the mechanism, then you need to be careful and look for the possibility of shifting a hydrogen or an alkyl group to make a more stable carbocation. Okay, because if you can, then you will. All right, so for example, you got this alcohol right here. So of course, we protonate that alcohol and then we form water, and then that water is an awesome leaving group, and so it leaves. Bye, Felicia. Okay, we get that secondary carbocation, which is totally a thing, right? We can easily form that. We do that. We've seen that before. We know this like the back of our hand now because we did SN1 and E1 reactions. And now if we think about it, we can shift that methyl group over. Just it's a 1,2 alkyl shift, right? So 1,2 shift between that methyl group. Let me draw it in red so that way it's more obvious. That methyl group leaves with its electrons, so that's why I have the bond highlighted in red on the bottom. And then what that does is that creates a tertiary carbocation at the spot where the methyl left. If you keep track of all of your bonds and your electrons, it only has 3 bonds, so therefore it has a positive charge. Okay, so this may occur in an E1 or an SN1 reaction because we always form that carbocation intermediate, right? So again, we've seen this stuff before. Now we're just introducing more or less a new concept that to make what we know a little bit more complicated, but also super fun. Okay, because we get to figure out this crazy puzzle, right? I told you it's like Sudoku on steroids, or like a Rubik's cube with like 27 sides or something. I don't know. Or just a regular Rubik's cube. Am I right? So look for beta hydrogen first on the tertiary position, or you can look for an alkyl group, and it's usually going to be like on a quaternary carbon, right? And the smaller that group, the better. Okay, so looking at the molecule on the left, we have that beta hydrogen on a tertiary. It's a tertiary hydrogen. We can shift that right over with its electrons. The middle molecule, we got a tertiary hydrogen that can shift right over as well. On the molecule on the right, we do have a hydrogen that can shift, but it's not a tertiary hydrogen, so we're not going to make it a better carbocation. We also have a quaternary methyl group that can shift right over to make a better carbocation. And so let's go ahead and draw these things out. So what happens when we shift that hydrogen over? Well, remember, it leaves with its electrons as well. So we have that H with the 2 electrons. That means that this carbon is positive on the left. Okay, it's a tertiary carbocation now. Now, we've got this particular substance that the hydrogen shifted over. We get the carbocation from where it left, right? And it's a tertiary carbocation. That's better than the secondary that it was. So now we're looking here. We've got, whoops, pressing weird buttons, my bad. We've got our methyl group shifting. Now it's, let me draw that in red real quick. So it left with its electrons, and wherever it left from, that's where you want your charge, okay? And that's what we've got here. You can tally up all of your hydrogen atoms and your carbon bonds or whatever. You can see that that carbon was trivalent and therefore positively charged. Now, if that hydrogen on the top left, it wouldn't do anything for us. And so that's why, obviously, we are not going to do that. Hydrogen 1,2 hydride shift is much faster than a 1,2 alkyl shift, though. Because it is smaller, it's an s orbital, so it's like non-directional, it's spherical. So there doesn't need to be a perfect overlap situation. Let me explain these molecules to you real quick, or why we get the products that we do for this particular alcohol, right? So let me, of course, we got that acid forming that oxonium ion, or water leaving, forming that secondary carbocation, right? So now we're looking for a tertiary beta hydrogen, right? So we got it right here. It's a 1,2 hydride shift, and we've got our location for that carbocation moved to that tertiary position. Remember that positive charge moves to where the hydrogen came from, right? So we remove that beta hydrogen, and we got our alkene product. Okay, so this is the weird one right here. This is the stuff nightmares are made of. No, I'm just kidding. It's actually really cool. I love it. So we protonate that oxygen, right? If you got an acid, you want to protonate something. Protonate the most basic site, okay? Then you have a oxonium ion, so it's a secondary position, so it can leave, and then we form that secondary carbocation, right? So how can we make this more stable? Well, we want to look at the beta position and see what we have to move around. So how did we get to the product, that 6-membered ring product that we had above? And so this is where it gets tricky, but if we highlight this red bond right here, this is an alkyl group, and it can move from one position to the adjacent one to stabilize that carbocation, and that's exactly what it does. Okay, so the way we draw this is, so this type of question, first let me tell you, is that we would probably just draw the mechanism of this particular sequence rather than like predict all the products. But maybe we could ask that because I'm introducing it to you, right? So you have to know that that's a possible option, okay? So let me number all of these carbons so we can keep track of our bonds. 1, 2, 3, 4, 5, 6. 1, let's just call that 1. And then on the 1 position, it has a methyl. Then we can call this 2, and on the 2 position, it has a methyl as well. And then we go 3, 4, 5, 6, 4, 5, 6. Okay, remember that sixth carbon moved from the 2 position to the 1 position. So that's our red bond there. And since it moved from the 2, that means that the 2 position has to have that carbocation, okay? And as you can see, it is a tertiary carbocation, so therefore it is more stable. We have a beta hydrogen available to remove, and then we can form that alkene product that we saw above and that we see right here. Okay, so that's the mechanism for this. It's called a ring expansion because you go from a less stable 5-membered ring to a more stable 6-membered ring. Okay, And so you can, let's take a look at this carbocation intermediate, right? You can do that, but why not just do like a 1,2 alkyl shift, right? Um, and then, so sorry, I forgot to write 1,2 hydride shift here. I forgot to write 1,2 hydride shift on all of these. I said it, but the proper notation would be actually draw it above that arrow. In a mechanism, when you're drawing it, you want to write that so that way any arrow movements are kind of not ambiguous. Okay, so we form this tertiary carbocation, and now we can do the elimination, right? And we can form these two alkene products, and then we obviously get that tetrasubstituted. Okay, so we do have two tetrasubstituted alkenes, but this 6-membered ring is more stable than a 5-membered ring. And so remember that from earlier chapters. And so that's why we might prefer to do this ring expansion to form that 6-membered ring. Okay, so there you have it. That's dehydration of alcohols with the carbocation rearrangements. Super fun stuff. Just break it down as simply as possible, okay? And then get that practice in. All right, bye. Okay, let me leave you with a little joke real quick. So this is my dog. He's a golden doodle. He's not a sheepdog. He's adorable though. So this sheepdog, he was like running around. He's gathering all these sheep, and he's like, "Hey, farmer dude, here's your 40 sheep." And the farmer's like, "But I only have 36 sheep." And he's like, "Yeah, but I rounded them up." What's up, sig figs in sheep form? All right, have fun, enjoy, bye.